Okay, so this is the second part of section 8.3, estimating a population mean using a confidence interval. We will in this part we will construct and interpret confidence intervals. We will use our four-step process in that, and whenever we're asked to create a confidence interval, we will also figure out how large a sample needs to be so that we will maintain a specific margin of error. That's the last thing. Remember in the previous section when we talked about the t-distribution and the need for the t-distribution, we saw that we have to replace sigma with s, the standard deviation of our sample, rather than the standard deviation of our population, because it's just not known. So the standard deviation of the sampling distribution, which we use as part of our margin of error, will be substitute out the sigma and put in the s, the standard deviation of our sample data. This means that we're dealing with the standard error rather than the standard deviation of the sampling distribution. Remember that this is why we use a t-distribution. When we standardize, it's no longer normal, but uses a t-distribution. Also remember that the degrees of freedom, one less than the sample size in order to get our critical t value. The inference procedure that we're using here, this is the second of many that we'll learn this year, is the one sample t interval for population mean, or for mu. It's similar in its approach to the one sample z interval for population proportions that we learned in the last section. Here emphasizing the fact that it's a t distribution, so we're saying a t interval rather than a z interval. All right, the formula that we use here for the confidence intervals, x bar plus or minus the critical t value times the standard error of the sampling distribution. Remember again, we're using s rather than sigma. All right, here's an example. Environmentalists and government officials and vehicle manufacturers are all interested in studying the auto emissions produced by motor vehicles. One major pollutant for gasoline engines is nitrogen oxide. Researchers collect data on nitrogen oxide levels in grams per mile for a random sample of 40 light-duty engines of the same type. The mean nitrogen oxide reading is 1.2675 and a standard deviation of 0.3332. These, of course, remember, are sample statistics. So this is our x bar, and this is our s, standard deviation of the sample. All right, here's the problem. Construct and interpret a 95% confidence interval for the mean amount of nitrogen oxide emitted by light-duty engines of this type. So we're trying to estimate what the population of engines of this type would emit as far as nitrogen oxide using a confidence interval. When they ask us to construct and interpret a confidence interval, that is your clue to using a four-step process. Okay, so here we go. State. We want to, here we're going to estimate what it is we're going to do. We're going to estimate the true mean or mean amount of nitrogen oxide emitted by the all light-duty truck engines. We're not estimating the amount coming from the 40 engines, but for the whole population of similar engines, we're using a 95% confidence level. The next thing we talk about is the plan. So what are we going to do to estimate this mean amount of nitrogen oxide? We are going to do a one sample t interval for mu, assuming conditions are met. Again, this is our second of many inference procedures, a one sample t interval for mean. The conditions that we're going to check here are the randomization. We randomly selected the 40 engines, the 10%. We can assume there's more than 400 engines of this type. And we have to look at the large count, or a large sample. Like, how large was our sample? Our sample was 40, which is larger than 30. The central limit theorem then says that our sampling distribution of x bar is approximately normal. So we are safe to use our t distribution calculations. All right, so we do our do. We first calculate our x bar. If that wasn't given to us, and that was, the mean was given to us, also was the sample standard deviation was given. So we need to calculate our critical T value, our degrees of freedom, one less than 40, the sample size is 39. So if we look at our row, look for a row 39 on our T distribution table, we'll see that it doesn't exist. We cannot pretend to have a larger sample than we do, so that's why we go down one to the next level on our table, which is 30. We use that in conjunction with our 95% confidence level column to give us our critical T value of 2.04. All right, we calculate it. Gives us an interval. We could calculate the critical T value using our calculator. You can notice that the resulting confidence interval is not too far off from what we calculated before. All right. Our final thing, that was so we did our plan, we did our state, we did our plan, we did our do. The last thing is our conclusion, where we interpret the confidence level, the confidence interval. And so we are 95% confident that the interval, and I just used the first one, 1.14599 to 1.3751 grams per mile, captures the true mean level of nitrogen oxide emitted by this type of light-duty engine. All right, the last thing we want to talk about is how to determine the sample size we need. Remember, we never want to use a larger sample than we have to, because samples cost money to run, time and money to run. So 3 things we have to concern ourselves with. First, we're going to get a reasonable value for the sigma from a previous study or from an earlier study or a pilot study. So the problem with not knowing our sample size, because we're trying to determine that, is that we also, number 2 here, we cannot calculate our critical T value since we don't know our sample size. We also don't know our degrees of freedom. So we resort back to a z-score. So we pretend like we're dealing with a standardized normal curve. So we do a critical z value rather than the T value. The last thing is we set that margin of error to be less than a certain amount that we want. So we set that formula less than or equal to a certain margin of error. Okay, let's look at an example. Researchers would like to estimate the mean cholesterol level mu of a particular variety of monkey that is used in laboratory experiments. They would like their estimate to be within 1 milligram per deciliter of the true value of mean at a 95% confidence level. A previous study involving this variety of monkeys suggests that the standard deviation of cholesterol level is about 5 milligrams per deciliter. All right, obtaining monkeys is time-consuming and expensive. So the researchers want to know the minimum number of monkeys they would need to generate and have on hand in order to satisfy this estimate, to get that margin of error as low as we need. Our 95% confidence, remember, since we don't know our degrees of freedom, we're switching over to our z-score here. Our critical z value in this case is 1.96. We know the sigma of 5 from past studies, and we get our expression that looks like this: 1.96, the critical z-score value, over the on top we have the 5, which is the sigma from a previous study, divided by the square root of n. We want that to be less than or equal to 1 millimeter per deciliter. All right, so we just got to solve this for n. We can move the n up, essentially bring the 1 down. We square both sides. We get an n value that is greater than or equal to 96.04. So we always go up. We never go down. If we went down to 96, then our margin of error would be possibly a little bit more than 1 milligram per deciliter. So we always go up. We don't round. We just go up to 97 monkeys. Okay, so here's your homework. Notice there are some 4-step problems, and then we have a couple of multiple choice at the end.